Okay, so we were talking about Boolean algebra in the previous class, and before we get started, or before we continue our discussion on Boolean algebra, we will just do some announcements. So homework 4 is due on Friday, October 2nd at 11:59 p.m. Studio 3 is due October 7th, and I hope that you guys are all using your time wisely to make progress on Studio 3. Later in the week, I will also post Studio 4 so that if somebody wants to get started on that, you have that option as well. Quiz 8 is available on Gradescope for you to answer now. Let's continue with where we left off. So the last thing that we talked about in the previous lecture was looking at this circuit and answering the question, what is its functionality? Now this is a circuit in which this is a logic diagram in which you have AND gates and you have OR gates and you have NOT gates as well. So it's based on basic gates. Now if you were asked to find its functionality, say for example, if you are asked to fill out the truth table, the one way of doing it would be to assume one sequence of inputs and then track all the way to the output and then fill the column for the output F. But that usually takes a long time and it is unnecessary, because what you can do instead is to write intermediate logic expressions. So for example, over here, the output of the OR gate over here is simply X or Y complement. And similarly, we did that for the other outputs as well. And then we eventually wrote the final output F as a logic expression. Now, clearly, this particular expression is not in a very standard form. So what we are going to do is we are going to try to manipulate this in such a way that we represent it in a standard form. So what I'll do is I'm going to go to the next page, and this is what we did earlier, where we said, okay, this is the expression for F from the previous diagram, and then we just distributed all the terms to write that function out as a sum of products expression, SOP. This is where things are getting OR of ANDed terms. So each term here is an ANDed term, and these are called product terms. And at the end, they are getting summed up or ORed together. So that's a SOP form. Now, before we go further, I would like to do a simple exercise where I convert this SOP form to a more standard form, which is called a canonical sum of products. So I'm going to simply take this guy from here and go to the next page, paste it here, and then look at F. So this is F, right? So essentially, I'm going to look at the product terms that are missing a particular variable. Am I missing anything on the chat? Why is my chat window not there? Oh, there it is. So I'll be talking more about the test soon, but today let's focus on the thing at hand. What are we talking about? We are talking about this expression and converting it to a canonical sum of product. So if you look at this particular term, the first term, X and Z, it is missing Y. So what I'm going to do is I'm going to force Y on top on that term without changing its value. So I can say this equals X and Y or Y complement and Z, because that is going to be Y or Y complement is going to give me 1. And similarly for Y complement and Z, I'm going to write that as X or X complement ANDed with Y complement and Z. And the last term already has the 3 inputs represented, either in true form or in complemented form, right? You see X is there, Y is there, Z is there. So it is already what we call a minterm. Formal definitions of these terms will be discussed in just a minute. So if I rewrite my function F, using this strategy, for the first term I have x and z, and I wrote that as x and y, or y complement and z, or the second term has y complement and z, and we forced x on top of that, so x and x complement and y complement and z, and then the last term was already a min term, so we left it as is. Nothing to manipulate there. Now when you expand it out, what you will get is every product term will have all three inputs represented, either in true form or in complement form. And that is what we call a canonical sum of products expression. So let's do this. X, y, z, x, y complement z, x, y complement z, x complement, y complement z, and the last term there. Now some of these may be duplicates, and we can eliminate one of them. So for example, if I look at this, this term is the same as this term. We only need one of them, so I'll just pick one of them and rewrite my last answer. So I'm going to write this and copy and paste, and then I'm simply going to eliminate this term because it's a duplicate. Now that is a canonical sum of products expression for f. So it's also called CSOP for short. Now, one thing to kind of quickly verify whether we did our work correctly or not is to recognize that there are 4 product terms. And how many ones did we have in the truth table? We had exactly 4 terms, right? So exactly where we had the ones, that's where we got our canonical sum of the product terms for our CSOP expression. Now, another thing to notice is we could have directly written it from here. So for example, if I look at the first one here, what do I have? X is 0, y is 0, and z is 1. So that will give me the product term x complement and y complement and z. The next one will be x complement and y and z complement. The next one will be x, y complement, z. And the last one will be xyz, because they're all 1. Now, if you look at these 4 expressions here, these 4 product terms here, they exactly match our CSOP expression. So that's how you can directly write CSOP expression from the truth table. You don't need to do the manipulation that we just did over here, but I just connected the two so that you can look at how it is connected. So the canonical sum just means the expression being expressed with having all terms including all variables. You got it? Yes. Now with this, let us try to essentially define what is a product term, what is a sum of product expression, what is a sum term, and so on. So let's see, what is a product term? So that 12 literals, all right. Is that 12 literals or are duplicates not counted? Duplicates are not counted. So this would be 12 literals. So let's see, product term. Okay, so what is a product term? Well, if you look at this, how many product terms do you see here? Well, I have one product term here, one product term here, one product term here. So you got 3 product terms, right? So any term which has a AND operation between variables, it is a product term. So examples, let's take a look at some examples. Examples would be x and z. Example would be x complement and y. Example would be x complement and y and z. Example would be a and b complement, and so on, right? So all those terms are product terms where you are ANDing inputs. It doesn't have to be all inputs being represented. It just has to be any input being represented. Also, if you have x, that is also a product term, right? So if you see this, x or y and z, right? So this is a product term. This is also a product term, and that would be a SOP expression, sum of product. So even if you have just one variable, that counts as actually both a product term as well as a sum term. All right, let me erase this out here and let's talk about the sum of product expression. We have already looked at it. We said it is SOP, right? Sum of products. What would be the expression? So for example, f equals x and z, or y complement and z, or x complement and y and z complement, the expression that we had earlier, that is an example of a sum of product expression. You've got product, 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 and then everything is getting summed or ORed, right? Next, sum term. What is a sum term? Well, in this case, you need, instead of having an AND operation between inputs, now you are going to have a OR operation between inputs. So for example, sum term, your examples can be x or y. A sum term could be x or y complement or z. A sum term could be a or b complement. All these are sum terms. So individual inputs being summed together, that's a sum term. A product of some expression. So let's see, POS. That is an expression in which you AND the sum terms. So for example, for f, let's use another function, g. G equals x or y complement and y or z and x complement. So I've written some arbitrary sum terms. These are my sum terms that I'm highlighting in yellow. Sum term 1, sum term 2, and sum term 3. And then at the end, after I did the sum of individual terms, I did a AND of all of them. So that is a product of sums expression, POS. What is a normal term? Well, a normal term, let's come back to the normal term at the end. Let's talk about minterm with n variables. So a minterm, as I suggested over here, right? A minterm is a product term in which all the input literals are represented, either in true form or in complement form. So let's just define it over here. So minterm is a product term in which all, and if it is n variables, all n variables are represented in true or complemented form. So an example of this, so let's see, we looked at 1, 2, 3, 4, 5 product terms at the top of this page. Which of these could be a minterm? Oh, no. So you see these product terms at the top, all of them except x. Well, even x could be depending on the entire expression. So you guys are going in the right direction. What matters is what are the n variables. So if I said there are only two variables x and z, then that is a minterm. If I said x and y are the only two variables, then even that is a minterm. If I said x and y and z are the three variables, then that is a minterm. But if I said x and y and z and w are the four input variables to this function, then x complement and y and z is not a minterm because w is not represented there. So it really depends on what you have to tell me the n variables that are involved in that, right? So only when you know the n variables, only then you can comment about which term is a minterm or not. So for example, if a function depends on x, y, and z, and it has the term x complement and y complement and z, then that would be a minterm. However, if the function is x, y, z, and w, then the same term will not a minterm. Right? So it really depends on what are the input variables that the function or the output of the logic function depends on. Right? So that has to be explicitly mentioned. Only then you can comment about whether the term is a minterm or not. But a minterm will always be a product term. So if a function only depends on x, so for example, if you said f equals x complement, or if you said f of x equals x complement, then even just x is a minterm. It will also be a sum term. It will also be, later on we'll see that, it will also be a max term. Now let's talk about a max term. The definition is pretty similar. It is just going to change in terms of product to a sum. So let's see, if I copy this guy here and paste it over here, come on. And then change this to sum, I am done with the definition of probably not this. So some term in which all n variables are represented in true form or complemented form. That is a max term. So all I would have to do in this is change the ands to ors. That is a max term. But the same thing, if the function has 4 variables, is not a max term. So max term is any term which is a sum in which all the input variables need to be represented. So all the terms in canonical sum of product need to be minterms. You got it. That's the definition that we are going to write on the next slide. Now, let's go back to the normal term. What is a normal term? Well, normal term is a term which is not a minterm or a max term. As simple as that. Not a minterm or a max term. It's called a normal term. So any logic expression will be consisting of either product terms or sum terms or min terms or max terms or normal terms. But that logic expression can be represented in 4 available forms: SOP, POS, canonical sum of product and canonical product of sum. That's what we are going to define on the next page. So let's see. Let's go here and define canonical sum of products. And like Andre already mentioned, it is defined as sum of minterms. As simple as that. And canonical products of sum is product of maxterms. Now, one thing that I want to kind of emphasize on is how do you indicate minterms? So minterms are denoted using small m. And max terms are indicated using a capital M. Now this is important because we are going to refer to minterms and max terms using the row numbers very soon. So all we can do is use minterms with a subscript of which is a number. That number corresponds to a row, a particular row in the truth table. That's how we can talk about minterms. So let's see. Let's do that over here. So here we have a truth table. There are 3 inputs to the function x, y, and z. And just to make our life easy and be able to write very compact expressions, what we did is we included a column for the row numbers. So we have a number between 0 and 7 denoting each particular row in the truth table. And for each particular row, what do? In order to find the output f, you simply evaluate that function with the inputs for x, y, and z as 0, 0, 0 and 0, 0, 1 and so on, right? So that would be the output column. So let me highlight the output column in blue. So you've got a black box indicating inputs. You've got a blue box indicating outputs. In this case, just 1. And you have got a row indicator, row column for row, just so that we can have numbers. Now, we saw this earlier, and we can see that now. The first row corresponds to a minterm, which is x complement and y complement and z complement. So if this particular term would be a 1, then that would be in f as a minterm. And the minterm subscript we can use is small m subscript 0. So I can just simply write this over here. Small m for minterm and subscript 0 for row 0. And similarly, I can write for this guy. For this guy, it would be small m subscript 3. And let's do max terms. What is here? Max term is capital M subscript 5. What is this guy? Capital M subscript 0 and so on, right? So you have got a relationship between a minterm and a max term that needs to be explicitly mentioned here. So I'll write it down over here. Let's see. So I'll say in general, any minterm, say m subscript k. So k stands for any row, right? Any minterm is simply the complement of that same max term. And consequently, you can also say max term or min term k complemented will give you max term k. And you can verify that very quickly over here. You see this min term 0. If you complement min term 0 and apply De Morgan's law, you go to x or y or z. That is your max term 0. So what is the reasoning for the complements not being in the max term? Well, they are there. It's just a different row. Because max terms are entries in the truth table that correspond to making the term 0. So if f is 0, if x is 0, y is 0, and z is 0, then x or y or z, that is going to go to 0. And x complement and y complement and z complement is going to go to 1. So max terms are essentially indicative of entries in the truth table where things are 0. And min terms are entries where in the truth table where it is a 1. Does max term must be 0? Yes, max terms, you will include those. So hold on to your questions for just a minute, because when we look at an example, it'll all fall in place. Right now, we are just talking about how to refer to min terms and max terms and what does that row number correspond to, which is becoming the subscript for the small m and the capital M. Now let's apply that to some examples to get some more clarity. Now, truth tables uniquely define Boolean functions. So when you are asked the question, what is its functionality, your first thought probably is, can I write out a truth table for this function? Because that uniquely defines the function. Now, using the truth table, you can come up with two standard or canonical forms, which is what we said earlier, right? Sum of product or product of sum. And then we can also convert that to canonical sum of product and canonical product of sum. That's sum of products is representing the function once. Function ones are included in SOP form, or you can also say canonical sum of product. And where the function is 0, that's what is called as the product of sum. And because it is canonical forms that we are talking about, canonical product of sum. Because in the truth table, you can only have ones or zeros. So that means that I can write every function using the ones, because zeros are going to be the places where it is not a 1. So one of the forms should work. So let's try to do that exercise for this particular example here. We are writing sum of products expression for on this slide. We are focusing on SOP expressions here. So you have an arbitrary truth table here. A, B, C are the 3 inputs to the function. The output function f is arbitrarily written 0, 0, 0, 1, 1, 1, 1, 1. Right? This is just an arbitrary choice. It doesn't correspond to any function. Just an arbitrary truth table. And for the sake of convenience, we are also writing an output column for f complement, where we simply invert or complement each entry in f. So wherever there are zeros here, it becomes a 1. Wherever there is a 1, that becomes a 0. Now using this, can I write the function as a complete expression? Let's take a look at that. So the question is, let's do it for f first. So we are doing it for f first. And if we are writing canonical sum of product expression, we are focusing on the min terms. Now min terms for what? If you are writing the output for f, we are looking at the min terms for f. Where are they? Well, where are the ones? So you would look at the ones and you would say, I see them right here. Those are the ones in my function f. So I would need to write those min terms for f. So what would be the first one? Well, the first one would be a complement and b and c. That's exactly what we wrote over there. Next, you would say, all right, there's another one here. When A is 1, B is 0, and C is 0. So that would be A and B complement and C complement. So that is right there. And similarly, you would fill out for all the 5 ones to get a complete expression that is already done for you. So this is a complete canonical sum of products expression for F. Now, you know, I really wish that I had some compact way to write an expression like this. Because just imagine if you had a truth table of the size 16 rows or 32 rows or 64 rows, then, you know, to write the complete canonical sum of product expression is going to take you forever. So you don't want that. You want an alternative scheme to do this. A more compact, a shorthand way to write the canonical sum of product expression. So let's write that over here, and this should make it very simple. For that, I'm going to include a row column. So let me use a different color, maybe green. I will write row here, and I will say 0, 1, 2, 3, 4, 5, 6, and 7. So just for the sake of numbering, I've written a row column here. I'm looking for a shorthand compact form for F. So let's write that in red. Function F depends on A, B, and C. I'm writing the sum of minterms, right? That's the canonical sum of product. So that would be minterm 3 plus minterm 4 plus minterm 5 plus minterm 6 plus minterm 7. And I can also simplify this to write it very nicely as summation A, comma B, comma C 3, 4, 5, 6, 7. That's it. So you see what I'm doing here? I'm just saying where are the ones in rows 3, 4, 5, 6, and 7. And if I'm interested in writing a sum of product expression, I would just say the summation sign. It is extremely important for you to mention the order of the inputs here, because as soon as you change the order of the inputs there, all the numbers get rearranged. So very, very important point, you have to mention the order of the inputs A, comma B, comma C, because if you change it, the numbers will no longer be 3, 4, 5, 6, 7. They will be something else. So that's how you would write it for F. And similarly, we have also written a complete canonical sum of product expression for F complement here. Let me show that in blue right here. And that is due to these 3 ones. So what I'll do is I will ask you guys to tell me what I should fill here. Summation A, comma B, comma C. This is for F complement. What should I fill here? Zero, 1, 2 is perfect. So you've got a complete canonical sum of product expression. You have also got a shorthand canonical sum of product expression. 0, 1, 2 is perfect. So complete is right here and shorthand is right there. All right, questions so far? Could you write sum from 0 to 2 for m of I. No. Don't. That's not like a standard notation. So let's, for logic expressions, it's not. So you use this. So if we were working with max terms, make max terms and F complement would be opposite. Yes. We will also take a look at that in just a minute. All right, so let's move forward here. This is essentially talking about the thing that we just derived. We did this in the previous one. This was the answer for the shorthand notation for F, and this was the answer that you guys said for F complement. We already did this. These are shorthand notations. Next, let's go to the product of sum expressions. Over here, we will be focusing on the max terms, right? So let me just write that down over here. Here we are looking for max terms or entries in the truth table that are zeros. Let's take a look. For the sake of convenience, again, I will add a row number 0, 1, 2, 3, 4, 5, 6, 7. And then let's talk about how we wrote the product of sum expression, complete product of sum expression. So let's look at F here and F complement there. Let's look at F first. So for F, which is right here, we are focusing on the zeros. How many zeros do you see? Well, you see 3 zeros. So I'm going to need 3 sum terms in my complete expression. So let's do it for the first one. I need it to be doing that. Let's do it for the first term. The first 0 for F happens when A is 0 or B is 0 or C is 0. That's how you get your first max term right there. Similarly, you have this guy, which gives you that. A is 0, B is 0, C is 1. I hope you are seeing the A is 0, B is 0, C is 1, right? So you're looking for all the zeros here. You're flipping the zeros. And then, of course, for the last one, for the last 0 in the table, we're going to highlight it slightly better, and I'm going to point it out. It's right there. A is 0, B is 1, C is 0. Now let us write, this is the complete canonical product of sum expression. It is canonical because each sum term has all 3 inputs represented. So each sum term is a max term, which is why I can say this is a complete CPOS. It is very crucial for you guys to take a few moments and identify these as either CPOS or CSOP. There have been many occasions on exams where the student incorrectly looked at it as CSOP, where the question was CPOS. So I want you guys to pay close attention to the terminology here. Next, let us write it in shorthand. In shorthand form, I'm no longer doing the sum, I'm doing the product. Let me use red. So I'm going to have a pi sign for product. I'm going to talk about my inputs in that particular sequence. Again, it is very important because I'm talking about row numbers here. And the row numbers that I would have to AND are 0, 1, and 2, corresponding to row 0, 1, and 2. And similarly for F complement, the zeros are over here. the expressions has 5 terms there, and in shorthand this can be written as pi a comma b comma c 3 4 5 6 7. So that would be your shorthand representation. Now, one thing that I hope you guys saw is that it is this. As you went from SOP to POS and between F and F complement, the things were complementary in nature. So let's try to elaborate that. Here you have the shorthand forms. We already talked about that. We already did that earlier. So let's talk about the relationships. For the same functions that we saw earlier, when we wrote for F the sum of product form, we had row numbers 3, 4, 5, 6, 7. That was the SOP form. And for the same function F, when we wrote it in the product of sum form, we had the row numbers 0, 1, 2. And I want you guys to recognize that complementary nature. Whatever rows are missed in one are there in the other. Similarly, when we wrote SOP and POS for F complement, we had 0, 1, 2 here and 3, 4, 5, 6, 7 there. Again, complementary. And the complementary relationship is not just for SOP and POS. It turns out there is also a complementary relationship between F and F complement. So if you look at this, if you just observe the SOP forms for F and F complement, there is a complementary relationship there. There's a complementary relationship there. So just to summarize, a function F, you can write that in canonical sum of product form, complete and shorthand. And you can write that same function in canonical products of sum form, complete and shorthand. In the same manner, you can do for F complement. All right, questions about this? How are we doing? So maybe I will write some cautionary note here. I will say pay attention. Pay attention to. One is CSOP versus CPOS. Many students over the years have gotten them mixed up. Not because they didn't understand them, because they didn't look at the question properly. The second thing I want you guys to pay close attention to is, what was that? The order of inputs. So when you're going for a shorthand form, explicitly mentioning the order of inputs becomes very important. And it's kind of very straightforward, right? Exactly the same as the order in here, A, B, C, A, B, C. So it's pretty straightforward to write, but you got to pay close attention to that. It matters. So if that information is not provided in your answer, then it is an incorrect answer. All right, it looks like you guys don't have any questions right now. I'm going to stop recording here.